Today we're going to discuss frequency modulation synthesis. Now, what is frequency modulation? Frequency modulation is when you take the frequency of a carrier signal, like we see here, and you drop the frequency like we see here and here, or you raise the frequency like we see here and here, depending on a modulating waveform. And you see this in broadcast audio for FM radio. If you ever listen to that in your car, I hardly ever do, but people are generally familiar with it. The other thing that you hear in is many audio synthesis techniques. And so we're going to go here in a few parts. Number one, I'm going to show a couple of things about the history of FM on Wikipedia. Number two, we're going to dive into a little bit of the math. Don't worry, it's not too bad, and I'll make it a bit simplified to ease our programming. And then number three, we're going to put it into a Jupyter notebook alongside all the equations, and then we're going to make a script that will beep it out the speaker, and then also write it to the disk in a sound file. I'm going to also make it in an atom file that is created in atom, and then saves the .py file, and then ran from the command line. So, with that in mind, let's get started. Frequency modulation is a major type of sound synthesis in music and other things. So it's been around for decades. And the frequency modulation synthesis page on Wikipedia is pretty good about this. It gives the history, it gives some derivations of equations. I like the equations. And where it's been used. One of the key places that was ever used was the Yamaha DX7. And so this DX7 was an iconic synthesizer widely used in the 1980s that kind of defined the sound of synthesized pop music. Which then brings us over to what is the math that we'll need to accomplish this. And it might look complicated at first, but bear with me. It's not as bad as it might look at first glance, and you'll get some really cool sounds out of it. I think that you can take this original Python script we make and just really go nuts with it. So a quick note as we look at the math. Frequency modulation and phase modulation are the two complementary principles of angle modulation. So angle modulation includes more generally frequency and phase modulation. We're not going to worry about the difference in this video. It is important from the math standpoint, but not important for what we're doing. More importantly is this graphic right here that shows a signal modulating a carrier. Now, so the carrier is of much higher frequency, several times higher frequency than the actual modulating signal. And what we see here is the signal at its trough widens the width between those peaks and troughs of the carrier, which drops the frequency. And at its peak, it does the opposite. It increases the frequency. This is in contrast to amplitude modulation, which I have another video on earlier in this sequence. And actually, you can combine the two to get some really wacky sounds. But we won't be doing that in this video. And so if we look at the math as it breaks down, we have a bunch of equations up here. We don't need to worry about those. What we do need to worry about is the sinusoidal baseband signal, because we'll just be simply modifying the carrier with another sine wave. So they'll both be sine waves. Which then brings us down to this equation. This is what we need to be concerned about. Now, this looks scarier than it actually is, probably. But once we just break it down variable by variable, we can easily put it into NumPy arrays and calculate the FM signal. If you don't have it installed already, let's go ahead and install the sound device library with pip. And what the sound device library will allow us to do is access the speaker from within Python. So, I can't type today. Pip install sound device. Notice that it has two D's on it. In the GitHub repository that I link to in the show description, you'll see the Jupyter notebook frequency modulation.ipymb. That's what this is called. And in this notebook, we have the equations and the Python that will actually make the sound file. So let's just breeze through this because I don't want to spend a ton of time on the math. Let's get down to the coding. But the basic thing that we get from Wikipedia has AC is the amplitude of the carrier, We leave it 1 in this demo. If you were to mix it in with other waveforms in NumPy, you'd want to change that, but we're not that sophisticated right now. AM is the amplitude of the modulating waveform, which the louder the amplitude is of that waveform, then the more frequency modulation effect you'll have. FM is the frequency of the modulator in hertz. FC is the frequency of the carrier in hertz. F delta is the peak deviation. And T is the time in seconds. That's a continuous waveform. However, since we're doing discrete samples with NumPy here, we need to change the equation up some. We need to add a couple more variables. Ti, which is the sample number, which is an integer. And so how many samples do we have? That depends on the number of samples per second and the duration of the waveform we are synthesizing. Fs is the sampling rate in units of samples per second. So, and then all the other same variables apply there. Now you're probably saying, yikes, that's a lot of math. And I agree. So let's go ahead and gather some coefficients, shall we? So instead of having this big blob in our equation, let's just make a deviation coefficient and call it k. So that's amplitude of the modulator times the peak deviation over the frequency of the modulator. And so now we can just adjust k, and the higher it is, the stronger the frequency modulation effect is. This is important right here because this is the carrier term. This is actually what defines the waveform of the carrier. This is the modulator term, which is what designs the waveform of the modulator. And so carrier term, modulator term, and then that all is wrapped inside the cosine function. And we even assume that AC equals 1, like I said above. We're going to do frequency modulation and sound device, which will play the sound out live. Yes, from within the Jupyter notebook. It's kind of interesting. And it writes out a wave file to the same directory which you launched the Jupyter notebook in. And it uses that simplified coefficient we just made, the k. The first thing we need to do is import the libraries, which of course is NumPy. scipy.io.wavefile import write. That gets our wave file writing. Sound device is SD. And then we import time as well. Let's go ahead and run that. If you know about Jupyter, you know that Shift-Enter will run that cell. So then these are the things, and up here I put the variable names. So Fs is the sample rate, is samples per second. Duration S is the duration of the waveform in seconds. So this duration is how long we want this waveform to be. Fc is the frequency of the carrier in hertz. Fm is frequency modulator in hertz. And K is our deviation constant, what we saw up here. And that has no units. You just crank it up to get more FM. So let's run that. And so now we need, so these variables up here pretty much just set up the parameters of our synthesis. Now what we can do is work on the actual synthesis itself. So these following lines synthesize the waveform. This is the real NumPy magic. So TIs is a NumPy A range. So that's the sample number for every sample we need to calculate. Carrier, okay. So notice this, because this is just the carrier term, 2 MP pi times TIS times FC over TIS, which is that. And then the modulator is going to be K, which is our coefficient that we created here, which we don't care about all this blob of stuff on the right side. We just care about turning K up. So it's just K times MP.sin of all that stuff. Then the waveform, remember I was talking about the carrier term and the modulator term, it's just MP.cosine of carrier plus modulator. And since we're assuming the amplitude of the carrier is going to be 1, that's all we need. So here's the next thing. After we calculate the waveform, which I will do by hitting Shift-Enter there, and ignore this little warning there, that doesn't hurt us. We're going to make something called waveform quiet. And that's going to be the whole waveform that we synthesize multiplied by 0.3, so it's a reasonable volume. So when you turn it on and play it, it doesn't blast out your speakers. So, and then we go ahead and convert it over to the format for a wave file, and then we write out the resulting wave file. There it goes. Now, if you're on now finally, the moment you've all been waiting for, we will play the waveform out of the speakers. All right, here we go. So there's the first beep. It's very raspy, and that's kind of indicative of some FM synthesis. But what can you do with it? Let's mess around with it for a few rounds, shall we? What I did is I took the liberty of pulling the Python code out of the Jupyter notebook and putting it to its own script as fm.py in the repository for this demo. I turned down k to 1.0. And so once again, k is the strength of the FM modulation effect. 1.0 is not very much. So let's take a listen to what happens with it. It sounds kind of rough turning on because this is a raw waveform that we're listening to. So nothing much there. But if I were to turn this up to 11, now some things are starting to happen. FM makes sound a lot louder. Almost sounds kind of horn-like. If I were to turn this up to 50, and if I were to change this maybe to 220, there we go. You can just mess around with these two simple numbers here, or three numbers, and get a variety of interesting waveforms. So that's kind of the beauty of FM. Some recommendations I'd have for you if you want to do further exploration is if you took this script and used one FM modulated signal to modulate another FM modulated signal, that can get you some really interesting things. And I'll leave that as an exercise for the viewer. If you want to see more of this more complicated thing with FM, I've done that before, but it'll require a longer video, so go ahead and leave a comment below. Thank you for watching this. I hope that you have fun with FM, and if you enjoyed this video, go ahead and look at the AM video in this series that I have, and the other videos I have on the sound synthesis. I think you could have a lot of fun with it. So with that, thank you very much, and talk to you later.